Hello and welcome to all of you in this lecture. As a part of TYBSc syllabus, we have got 4 chapters. So, we are going to start with the first chapter, that is polycyclic aromatic compounds and some heterocycles with one hetero atom as a part of them. So, to begin with, let us do the introduction part. So, heterocycles or heterocyclic compounds are those where at least one element other than carbon is there. So, normally nitrogen, oxygen and sulfur, and accordingly they are different compounds because they are biologically important. For example, furfural, the 2-formylfuran is a precursor for nylon. Pyrrole is found in hemoglobin and chlorophyll. Thiophene is a part of vitamin H, and 8-hydroxyquinoline is anti-malarial and anti-amoebic medicine. And beside these, there are so many heterocyclic compounds which have got medicinal values, and that is why it is essential to know about the heterocyclic compounds. So, as I said earlier, heterocyclic compounds are those where carbon is replaced by at least one heteroatom. So, in your syllabus we have got naphthalene, anthracene from the carbocyclic compounds, and furan, pyrrole, thiophene, pyridine. So, these 4 compounds are there, but to understand the classification and nomenclature we have to go through these, the naming method for these heterocycles, and then we have to look at the polycyclic aromatic compounds also, wherein the arrangement of rings is different. So, to begin with, the 3-membered oxygen containing ring is named as oxyren. In normal language we call it as ethylene oxide, and this is aziridine when oxygen is replaced by nitrogen. For 4-membered it is known as oxytane with oxygen. For 5-membered it is pyrrolidine. 6-membered is piperidine. The relative position of oxygen is 1,4. So, this is 1,4-dioxane, tetrahydrofuran, morpholine. This is pyran, the 6-membered ring. Imidazole when 2 nitrogens are there, 5-membered. 6, that is pyrimidine. Then if X is oxygen, that is furan, X is equal to NH, that is pyrrole, and X is equal to S, that is thiophene. These are common names, but generally these are used. Then 6-membered ring, pyridine, quinoline, isoquinoline, indole, and there are so many, but that may not be the part of your TYBSc syllabus. So, let us restrict ourselves to these. Then there is one system for the nomenclature of this thing. So, ring size, saturated and unsaturated. If 3-membered ring is there, it is arene. So, oxyrene, then 4-membered is ethane. So, that is oxytane. Then olane, enane, epane, ocane, onane and ecane. Unsaturated are irene, ete, oli, ene, epine, ocine, onine and ecine. So, these are the nomenclature by Hans. Normally, these compounds are known by their trivial names, common names. Okay. Now, let us talk something about the polycyclic compounds. Now, polycyclic means this benzene is basic compound and this derivatives. This is naphthalene where 2 rings are fused. If the rings are 3, that is anthracene, If the arrangement of the third ring is different, it is phenanthrene. If 4 rings are there together, that is naphthalene. If 5 are there, that is pentacene. If the arrangement of 4 differs, that is known as chrysene, and this is pyrene. So, these are all, like, you have only these 2 compounds in your syllabus, and normally we have to look at their properties and electrophilic and nucleophilic substitution on those rings. So, that is the objective of the syllabus. So, let us look at the reactivity part, and now we will focus on the syllabus part, because the compounds which are there in the syllabus, we will talk more about them. So, let me clear the other part which is not necessary to study the electrophilic and nucleophilic substitution part. So, let us focus on the 5-membered rings, the aromatic ring. Now, the aromaticity is because of the lone pair of electron of the heteroatom. Now, this lone pair is available for donation, and according to Huckel's rule, it has got 4n plus 2 pi electrons, 6 pi electrons. So, for n is equal to 1, this is aromatic. So, these compounds, let me put the first example. This is furan. Now, furan, thiophene, furan, pyrrole and thiophene. Amongst these 3, pyrrole is more reactive than furan, and furan is more reactive than thiophene. So, that is about the reactivity. And for the electrophilic substitution, let us talk about the furan. So, let us concentrate on first molecule. So, what type of electrophiles can substitute the nuclear hydrogen? Because they are aromatic, they have got some stabilization energy, the resonance energy, what we call it as, in it gives the additional stabilization by the virtue of resonance. And now here the resonance is solely because of the lone pair which is available with the heteroatom, and you can write down the resonating structures for this. The numbering goes like this: 1, 2, 3, 4 and 5. 2 and 5 are equivalent, so as 3 and 4. So, these are the 2 position, and accordingly we can write down the let us say that electrophilic substitution is taking place at C2 and C3. So, as a result of this, what happens is, so at 2 position we are putting electrophile. So, 3 becomes electron deficient. So, it is like this, and alternatively when 3 gets substituted, 2 becomes electron deficient. So, this is one thing. In addition to this, you can always put the canonical structures. The positive charge is shifted here. You can write down one more resonating structure by utilizing the lone pair of electron, and now the excess charge is taken up by oxygen, and then lastly this proton is sacrificed and you restore the aromatic sextate for this compound. Okay. Now, this is about C2 substitution. If C3 undergoes substitution, the next thing is this will be stabilized by the participation of electron pair from oxygen, and lastly you have to sacrifice the hydrogen, so that the aromatic sextate is restored. So, you can show it like this. This hydrogen comes here, this goes here. So, positive charge on oxygen is neutralized, it is rectified. So, the relative stability of the villain intermediate is more when the electrophile attacks at 2 position, or when this carbon number 2 proton is replaced by the electrophile. So, first, second, third. So, 3 canonical structures, valid canonical structure for that intermediate, whereas here we have got only 2. So, 2 against 3. So, naturally the transition state or the intermediate which has got more stabilization by the virtue of resonance is more here, more in this case than second. So, the statement goes like this: the transition state or the intermediate resonance stabilization of 2 substitution intermediate is greater than that of 3 substitution intermediate. Now, they are not saying villain intermediate and all, but we know that these are villain intermediates or rhenium ions, that is another term which is used. So, C2 substitution, C2 electrophilic substitution is preferred. If one of these two is substituted, the electrophile will go to another site. If both are substituted, then 3 and 4 can be also substituted, but those cases are less, but nonetheless that also is possible. So, for all electrophilic substitution of 5-membered ring heterocycles preferentially takes place at 2 position. So, I am going to put some example for the illustration, and let us put some example wherein you can easily talk about electrophilic substitution. Since the compounds are aromatic, we often call it as aromatic electrophilic substitution on the heterocyclic system. So, let me put one example wherein your heterocycle is subjected to electrophilic substitution. So, furan, then HNO3 and acetic anhydride. NO2, not this, NO2. Okay. Now, that means it is 2 substitution, and now we are using this nitric acid and acetic anhydride. So, in C2 what happens is this OH, NO, this is HNO3, and now when this attacks on acetic anhydride, you get acetyl nitrate. So, that is the first reaction. CH3 CO OH, and the other entity is CH3 CO O NO2. It will be positive. Now, this is acyl or acetyl nitrate. Or you can say acyl nitrate also, no problem, but this is the actual species which is generated, and that is the species for nitration. So, what happens here is, I will just put it here. Then you can show it like this. to show the delocalization. So ultimately what happens, how does it look like? Plus N double bond O minus, and now the OHC minus which is coming out can also function as a conjugate base, and eventually you get the substitution at 2 position. So this is acyl nitrate which is prepared from this combination, and that becomes a very good nitrating agent. We cannot use HNO3 H2SO4 combination because this ring is labile to so strong acidic condition. That's why this is the reactive intermediate, or this is the actual electrophile which is generated in C2, and that is the electrophile which is generating NO2 plus in C2, and then acetic acid is byproduct, that is also weak acid, so not a problem, and the acidoxy group also helps in the abstraction of proton from this thing. So acylation, the nitration is one reaction. Now let us talk about other reaction which is possible or in with this kind of substrate. So nitration, sulfonation, acylation, whatever reactions we are talking about, they are possible with this heterocycle, because this is again I will generalize it RCOCl and aluminum chloride. Now we are talking about the Friedel-Crafts acylation reaction, because herein we are going to talk about the acylation. So this is Friedel-Crafts acylation, similar to benzene. This is also aromatic substrate, and then the first foremost thing is you can generate the ion pair CO plus AlCl4 minus, the intimate ion pair what you call it as, and then in next step you can directly show with this, or you can take the help and put it this way. This is plus, and eventually this will lose the proton to AlCl4 minus, and you can get the desired compound wherein 2 position is substituted by electrophile, and once again you get the release of AlCl3, that is a catalyst which is generally used for Friedel-Crafts alkylation and acylation reaction. HCl is lost as a byproduct, and of course the same AlCl3 can complex with another acetyl chloride or this acyl chloride, and the same reaction will continue from here. So that is the Friedel-Crafts acylation reaction. So in general the second position is substituted, and the various electrophiles like nitronium ion, acylium ion, even alkylation, halogenation, the diazonium coupling, all these reactions are possible on this kind of substrate. And the only problem with furan and pyrrole is you cannot use higher acids like H2SO4, HNO3 concentrated, because furan is known to undergo polymerization under highly acidic conditions. So the optimization of reaction condition is mandatory here. I will just put one example, and maybe next time we will continue from here. Yeah, I will just put one example here. 2 molecules of this and KCN, alcoholic of course, and the product also I will put CHOH, CO, and then another ring is there. So this is your benzoin type condensation, benzoin condensation reaction. So with furfural, now this is furfural, 2-formyl furan is known as furfural. Furfural will undergo this kind of condensation, which is benzoin condensation, and this compound is known as furan. So this kind of reactions are also possible. So we have to be careful, because this kind of compounds, electrophilic substitution, nucleophilic substitution, everything we have to see, but one by one we'll go ahead. So with this substrate we have to see some more electrophilic substitution reactions with varying substituents on the ring. We are writing say plain ring, then one monosubstituted, then disubstituted. So that's why the orientation and reactivity part. So substitution at 2 is nothing but the selectivity, that is the orientation of the incoming electrophile, and if the substrates are like substituents are more, then also we have to talk about the regio selectivity of the electrophilic substitution. So that's all for today. We'll continue from here, and we'll try to cover up the basics, because that is mandatory, and then we are going to talk about the relative reactivity of all these compounds under acidic condition, what happens, how it will undergo polymerization and all. We'll see all those things maybe in next lecture. Okay. So thank you very much.